In this video, we're going to look at how to deal with limiting reactant problems. So we're going to use what's called an ICE chart. Moles at the beginning is I, initial, C is change. Actually, this is F. This is an ICF chart. F is for final. Where do we end up after the reaction proceeds to finality? First thing we need to do is identify how many moles of each reactant we have at the beginning. That would be our first row. So hydrogen, let's see, we have 10.10 grams of hydrogen. Hydrogen is 2.02 grams per mole, so without using a calculator, we should see that 10.10 divided by 2.02 is 5. These should be calculatorless. So I'll have 5 moles of H2 will go here. You could write that in, or you could wait until I open this up. The oxygen, we have 64 grams of oxygen. And oxygen, O2, is 32 grams per mole. So to get to moles, we divide the 64 by 32, and we get 2 moles of oxygen. So here's our first row. Now, so I have initially 5 moles of hydrogen, 2 moles of oxygen. Notice I did not look at the coefficients here at all. Now on our next row, we're going to look at the coefficient, the change. How much does the hydrogen change by? This little x, it's called the extent of reaction. It would be how much would react if a chemical had a coefficient of 1. So x will actually be how many moles of oxygen react, because oxygen has a coefficient of 1 in front of it. So for the hydrogen, this would be 2x. Oxygen would be 1x. The water would be 2x. Now the next question might be plus or minus. Let me show you. We have minus 2x because of the 2 moles of hydrogen, minus 1x because of the 1 mole of oxygen, and plus 2x here because of the 2 moles of water. So why minus and plus? Well, if the reaction is going to the right, and we have reactants reacting, the reactants obviously decrease. So that's why we have a minus on here and a minus on here. The products are increasing, so I would have plus 2x right there. Okay, so the change row is pretty easy to figure out. This part might get a little complicated or confusing. It's not complicated to do it. What you do is just you add the first and the second rows together, so that would be 5 plus negative 2x, which is the same as 5 minus 2x. This would be 2 minus x. This would be plus 2x. 0 plus 2x, which is the same as 2x. So we would start with that. You'll see this a little later. And we set that equal to 0. The instructions are right here. Add the first 2 rows, set equal to 0, solve for x. The smaller x wins. Okay. Oh, and we don't need that. So when I solve this for x, I get, for the hydrogen, x is 2.5. For the oxygen, x is 2. These x's, remember again, are the extent of reaction. How much would react if the coefficient were 1 for a chemical? As soon as we get to some chemical completely being used up, the reaction must stop. So the smaller extent, whichever x is smaller, remember x is the extent of reaction, the smaller x is what x will be. So when we calculate x for each of these, we find that we have a 2 and a 2.5. 2 is smaller than 2.5, which means the extent of reaction is 2. I don't want to move that. And I will use x equals 2 to solve for the actual amounts of each chemical that are left over. So here we go. So I have 5 minus 2x. X is 2, we just learned, because 2.5 is less than 2. So I substitute that smaller x back into my original equations up here, and I get 5 minus 2x equals 1, which says I will have 1 mole of hydrogen left over. This oxygen amount, 2 minus 2, is 0, so I have no oxygen left over. Now for the water, I get 2 times x. 2 times 2 is 4 moles of water created. So the original question was, what mass of water will be made? I now have all the moles left over or created, and I can convert moles into grams. And the question said, what mass of water will be made? So I have to go all the way to moles. So for water, I have 4 moles of water, and I just convert my 4 moles using stoichiometry into grams of water. And then sig figs. Now, 72.1 or 72.0 would both be correct and acceptable. The sig figs get a little iffy here, but originally I started with 3 sig figs and 4 sig figs. I'm doing some subtraction and addition and some multiplication division, so again, I'm not going to be too picky on sig figs here. But since oxygen is the limiting reactant, the amount of water made will depend on the oxygen, so I should keep 3 sig figs here. And this is the mass of water made. And we could have done that without a calculator or with a calculator. Now part B, what is the limiting reactant? We already learned that. Here's our 0, no oxygen left over. Oxygen is our limiting reactant. And finally, what mass of excess reactant will be left over? Well, I have 1 mole of excess reactant left over. So 1 mole of hydrogen. Hydrogen was the excess reactant. I have 1 mole of hydrogen, and the molar mass of hydrogen is 2. It's really, we can use 2.02. The only reason why I went to 4 digits here is because I started with my 4 sig figs for the grams of hydrogen. So when I'm calculating my final amount, I'm using the 4 sig figs. Again, we did some subtraction here, so really for x we only had 3 sig figs. X is 2.00, so I really here would say I have 1.00 moles of hydrogen left over because of this subtraction here. And that number 2, this x equals 2, truly had only 3 sig figs. So in reality, I should write this as 2.02 grams of hydrogen left over. And that is how you do this. And just a quick recap, you only need to do this box when you're asked about limiting reactant problems. It's very simple. You calculate your moles of reactant, and then you fill in the change row. You calculate what x would be by you add up the first 2 rows, set them equal to 0, solve for x, smaller x wins. And then you plug that smaller x back into this equation right here, and that gives you the moles left over or created, and from that you can calculate everything else. The instructions are all right here for each of the charts when you have an actual, for the in-class work. When you have an actual test, obviously you won't be given all this information, but hopefully you'll have enough practice that'll just make sense.